Hello everybody, today I'm talking about the shortest path problem, which is one of the most important optimization problem and that is very common in geographic information system, for instance. Okay, so let's try to think a little bit about the problem that we have at hand. We have here a network, right? As you can see, there are different links or edges and you have different nodes or vertices, something that I've talked about earlier. Oftentimes, one of the things that we want to do is to go from an origin, here I put S as being the source node, to a destination that I put here as terminal node. Okay? And the question that we have in the shortest path problem is to try to find the path of least resistance or maybe of least impedance, for instance, least cost, least time, least distance, whatever that impedance is. And you would calculate, essentially evaluate all the combinations, and then eventually maybe you'll find out that, okay, well, the best path here is, maybe something like this, okay, maybe something like this, maybe something like this, and something like that. One thing that is very important to notice is that each of these links that is selected, or all of them in fact, have to have some sort of cost. It could not be that you get a reward to use that particular path or that particular link, sorry. So all the costs have to be positive. So let's think a little bit about the problem. Our input is given a network with cost associated with each of the links. So there is a cost to travel that link, okay, and that cost is Cij. So what is Cij? So if I have here a particular link I, okay, and this is J, here that's the destination, right, and then this can continue later on, this can continue also, that would be the cost to travel. Very simply, in GIS or any other software, you could simply assume, for instance, that the distance, Dij, is actually the cost. So that would be one way to do it. But of course, there are better measures for that impedance. So given that network, find a shortest path or a least cost path, right? Whatever, again, the cost is, from a source node, S, okay, to a terminal node, T, okay? So what are we going to use in terms of input to make that happen? We're going to use Cij, which is the cost to travel from I to J, and then we have a decision variable Xij, which is equal to 1 if link Ij is on the shortest path from S to T, okay? Very important. And then 0 otherwise. So that's kind of the input. And now we are going to talk about the formulation. So our inputs here are the cost to travel from I to J. So this is again a link on our network, and Xij, which is a decision variable that is equal to 1 if link Ij is on the shortest path, okay, from S to T. So for instance, that link is on the shortest path, and 0 otherwise. Okay. Let's have a look at actually the formulation, which is actually very short and quite simple. So I have here a minimization. We're trying to minimize the cost, okay, of Cij times Xij. So we're trying to minimize the total cost of traveling, okay, by summing up every link that is on the path. And here this constraint is quite important. We're basically saying that every incoming link that goes to I minus any outgoing link, so Xji, J here is here, that is J, and go I, so this is every link here minus every link here, right, should be equal to 0. So there should always be an incoming link and an outgoing link, unless, okay, the node here, this one I, is the source, because in that source there is no link coming in, there's only link going away from it, so that's why it should be -1. And here for the terminal node is a receiving link, there are no links that are leaving, so therefore they should be equal to 1. Now this is very important, okay? And then of course you have here this Xij should be of integer nature, to make sure that we're not traveling maybe half of the path or a quarter of the path, okay? And again, as I had mentioned earlier, but I think this is very important, the cost here should always be either 0 or positive. Why? Because if they are negative, right, then there is a reward in cycling, and we really want to avoid that. Okay. So now that I have shown you here the sort of the formulation and the background, I'd like to show you a small network and work out the entire formulation for that one, and then we will solve it in Cplex. Hello everyone, I'm going to show now how to solve this problem, the shortest path, with the formulation that I talked about earlier. We have here a network with a total of 6 different nodes, 1, 2, 3, 4, 5, and 6. And in orange you see the cost to go from one node to another one. So for instance, from 1 to 2 it's 7, from 1 to 3 it's 8, and you can see all of those are positive, they are not negative. Okay, so let's work out our entire objective function we're trying to minimize. Now if you see here, very important, it's minimizing the cost of going from 1 to 2, but also possibly from 2 to 1. Now we'll see later we don't actually use 2 to 1, but we don't know. And it's always the same, so it's C times xij plus cji times xji, okay? And you do this for every single possible link that existed. Again, you can calculate that in a GIS relatively straightforward. Now this one is quite important, right? This one here, excuse me, let me go on the other side. This is here to say that x31, x31, okay, plus x21, okay, minus x13 plus x12 should be equal to minus 1. So here is to say that, you know, the sum of these links that are going to 1 minus the one that are going away should actually be minus 1. So there should actually be at least one link that goes away. And similarly for the other nodes here, if you do the sum of the outgoing links minus the ingoing links, then that should be equal to 1. Okay, and then for each of them, you are going to see here, for instance, for 3, you're going to see the links that are going to 3, okay, minus the links that are leaving 3, so x2, x31 plus x32 plus x34, okay, the ones that are leaving minus the one that are coming should be equal to 0. So there should always be here a zero sum at the end, and right, and you would repeat. And then the very last equation here are integer constraint requirements that we are going to enforce. So what I'm going to do, I'm going to solve this one in Cplex and see what the solution is. But I am pretty sure that the solution would look something like this, right? 7 here, and then 5 here, okay, and then 10 here, for probably a total sum of 22. That would be my guess. We will see this in just a second once we solve this in Cplex.
All right, we are now in Cplex, and here, before I solve the problem, I just want to show you what the LP file looks like. You can see again the minimization function where each link is, can go in both directions, as you remember. It's a pretty long objective function for such a small problem. Subject to, so these are the links that are going in, so the first one here, the links that are going in towards 1, minus the one that are leaving should be equal to minus 1. So here this equation guarantees that there should be links that are leaving 1, not going to 1. And here as the opposite, so if you sum up the links that are going in minus the one that are leaving, this should be equal to 1. And this is for the terminal node 6 that we specified. Okay, and the rest of the equation, this is similar to the blackboard I just explained. And then you have binary variables, which are essentially binary integers, sorry. So that's good. So let's go into Cplex. So I'm going to do here read, and this is the name of the file, shortest path here, LP. Okay, and I optimize it. I have a solution of 2.2 to the time 10 to the 10 1, so that's 22. And if I want to display the solution variables, okay, and all of them, it will tell me that 1, 2, 2, 5, and 5, 6 are selected, and again from there you could then recreate the entire path. And so as you can see, this is similar to the solution that we obtained earlier.